So there are people on- Okay. Cool. So sorry about that. As always, math things run on math club time, which is 5 minutes after, so I apologize. But thank you all for being here. This is, I think, the first ever, at least since I've been here, course information session, or at least of this scale. So we really appreciate you all. We have a lot of sort of great faculty, a lot of great courses that are being sort of advertised and talked about today. But before we jump to that, just a couple of things. For those who don't know, I'm Nick May, and I'm a student here. This meeting is also hosted by Zach Greenfield. So he'll be speaking a little bit later. And we just want to give a huge shout out to all the faculty and staff who sort of made this event possible, specifically Professor Spolika and President Dummett, as well as Professor Schulte, Beth Kuda, and really everyone else who made this happen. So again, we really appreciate you being here. For those who are wondering what this is, right, you see the term course info session, but specifically what we're going to do is we have between 8 and 10 faculty, and we're going to be talking about a variety of courses sort of over the next hour and a half or so. Each person's going to spend maybe 5-7 minutes talking about the courses, maybe less, totally up to them. But certainly there will be time between each sort of course that's being talked about for questions. And so that's really what this session is for students to ask questions. If you have a question about course logistics, or if you want to hear like a student perspective, there are a lot of students who have taken these courses as well here. So definitely don't hesitate to ask. As you'll notice, everyone's emails are up on the board right now too, and they will be up later on as well. So certainly if you have like any specific questions, you want to send people emails afterwards, we highly recommend it. And if you're not really sure who to ask, or like you're trying to find a student who maybe was taking the class or things like that, feel free to email Zachary. Our emails are up there as well. Then we can put you in contact with whoever you want. I will also take this opportunity to plug a student department social that is happening next Wednesday at 4:30, between 4:30 and 6 in 553 Lake Hall, which is the Math Lounge. If you've never been to the math department before, and I know there are some of you still, COVID really messed a lot of things up. But if you haven't been to the math department before, it's a great opportunity to go figure out where the Math Lounge is. But that'll be another opportunity where a lot of faculty will be there, as well as hopefully a lot of students. We will have pizza, a little bit more substantial food, I should say, offerings as well as drinks. So again, come hang out. Nothing too stressful, super laid back. We would highly recommend it. We'll be sending out in more formal announcements in the next day or two. So with that, we'll sort of be interrupting, throughout the sort of next hour and a half, just with random tidbits of information. But our first sort of, if no one has any questions, we might as well get started jumping into it. So our first speaker of the afternoon is Professor McEllen.
All right, so I don't really know what I'm doing, being the first speaker of the first session, but I do know what I'm talking about. So this is the course Math 3341 Dynamical Systems. We use this great book by Stephen Strogatz. So we cover a lot of different topics. We start with dynamical systems, 1D, 2D. So you will have seen differential equations and systems if you take 2341, which is a requirement for this course. I think it's probably best if you've had that before you try to take this. So we do talk about attractors for one-dimensional dynamics and bifurcations, which is when you have a dynamical system that depends on a parameter and you vary the parameter, and the attractors can appear and disappear, their stability can change. So that provides a very interesting phenomenon. We also, in 2 dimensions, see different kinds of attractors, like limit cycles rather than just critical points. And then eventually we start moving away and looking at chaos. So the other kind of theme of the course is chaos. The name of the book is Nonlinear Dynamics and Chaos with Applications to Physics, Biology, Chemistry, and Engineering. And there's lots of applications, so it's really interesting to see some of the mathematical theories really represented in these different fields, and often get a lot of different majors. So I think it is very, has a lot of appeal to interdisciplinary fields. And so we look at chaos. in the context mostly of dynamical systems, that is differential equations systems. But then we also do a little bit with iterative maps, including the logistic equation. And then that naturally leads to the question of what kind of attractors can you have when you have chaos. And so you have these strange attractors, like come up with the Lorentz system. And so that gets us into kind of strange objects like fractals. So we spend a certain amount of time looking at fractals, both the self-similar kind, which you've probably seen from Cantor's set, Cox snowflakes and things like that. But also something like the strange attractor for Lorentz equations, for Lorentz systems, which is not self-similar, and so you have to talk about its dimension in terms of a correlation dimension. So we get into that. And that pretty much sums it up. So maybe I'll just open the floor to questions. Yeah.
So going from a differential equations course into this course,
Right.
Do they have a similar like approach? Like I know in differential equations course, you go in, you have a problem, and you say, how do we approach this? How do we solve it?
Mm-hmm.
Is that also the kind of approach you take?
Well, we don't do very many, looking for a solution formula. We talk about qualitative behavior. So if we start with chalk here, if we look at a simple equation, first order equation, like x dot is equal to x squared minus r, or minus 1 to begin with. So, you're going to have two critical points at -1 and +1. And if you look at the dynamics here, so the trajectories are going to be doing this. And so you have a stable critical point here and an unstable one here. So that's sort of qualitative analysis we're doing. We're not trying to solve this explicitly using separation of variables or anything like that. Other questions? So I should say Nick was a student of mine in this course.
Highly recommend it.
Yeah.
It's an amazing class there. But I will sort of just ask a general question.
Yeah.
Oftentimes I know, a lot of people will take sort of, mid to upper, level advanced courses in preparation for like a capstone of sorts, applied math, research capstone, things like that. Obviously this is, this course is sort of, you're learning the fundamentals effectively, but are there, have there been students in the past who have been able to sort of take, what they've learned and, something like dynamical systems to then sort of, more apply it to a capstone type thing or an independent study?
So yeah, I don't know so much about this particular course material, but dynamical systems is often used in capstone because there's lots of modeling opportunities with dynamical systems. So yeah, it's good background. And I think there are a lot of good project ideas coming possible with this course. Yeah.
What is your favorite dynamical system?
Oh man, let's see. I don't know. I think in this course, I mean, I really enjoy teaching this course because of all of the different applications. And one of the first places they talk about bifurcation is in a laser threshold, where they have this light as it increases in intensity, it eventually crosses the threshold into laser light. And just to see that, trying to reduce the very complicated physics down to a simple enough dynamical system, you can analyze and actually see that bifurcation as a transcritical bifurcation is that's cool. Anything else?
Thank you so much for talking.
Sure.
Anyone thinks any more questions after anyone's talked? I'm sure there'll be time at the end of the presentations to ask more questions, follow up, and also we have the social next week, and feel free to email either us or any of the speakers today.
I want to add to Bob's answer, if you don't mind, because I've actually used some of those models from Strogat, which is a great book. By the way, on modeling. I can tell you what my favorites are. And there's the one's just in the exercise, the rock, paper, scissors dynamics.
Oh yeah.
And I also like the outbreak model, where a predator gives up on one prey, moves to another prey, and then the first prey, there's an outbreak of that, causing, in this case, destruction before us. So really, there are many others.
Yeah, there's lots in the book.
So that helped advertise your
Thank you. I'll
Thank
return
you.
the favor.
Right, but I'm not sure.
I believe we have Professor Weisman talking about complex variables.
Now you have the blackboard.
Yes.
Just to be pointed out.
You can do it.
My friends in the humanities are always making fun of us mathematicians. We can't talk without having the blackboard. What can I do? That's the way we're going. So the course I'm advertising is math 4555, and that's functions of a complex variable. And put it in a nutshell. Put it in a nutshell, we repeat everything you've done in calculus, but with complex functions of complex variables instead of real functions of real variables. And so for the first half of the course, we just review calculus, doing every single thing you've done in the 3 terms of calculus, but for complex variables rather than real variables. And for the first half of the course, it all seems like just the same. And then somewhere in the middle of the course, where we come to integration, all of a sudden it becomes completely different. And the advertisement for the course is it's much simpler. And all sorts of things that are almost impossible functions of real variable become almost a joke for functions of a complex variable. So I want to, so the idea of doing calculus for complex variables sounds insane. In fact, the idea of having complex variables sounds kind of unmotivated. I mean, I'm sure you've all seen complex numbers in high school, is that correct? But the idea is, well, you declare some number whose square is -1, and then you do stuff. Right? So let me try to give you some motivation as to why that might be something reasonable. So I can give you a motivation from algebra, from geometry, and from analysis. We'll try to go through all 3. I think I could probably do it in 5 minutes. So the first one is from algebra. And that's, as you know, if you start, I mean, the most natural numbers are the natural numbers, 1, 2, 3, and so on. And then you can have the integers. You might believe that there's such a thing as 0 and negative numbers, although it took people a long time to invent them, right? But if you write a linear equation in natural numbers, such as 3x equals 2, or even with coefficients in real in integers, the solutions require you to concoct the rational numbers, right? Because the solution to this is x equals 2/3, which is no longer an integer, even though this linear equation had integer coefficients, right? If you now go to higher order equations, you may have to have rational numbers, you may have to have irrational numbers, or maybe even real numbers. But what happens if you try to solve polynomial equations? Things of the form x to the n plus a to the n minus 1, x to the n minus 1, plus dot dot dot, plus ac. Well, over the real numbers, so let's assume the coefficients are all real. So if see here, integer coefficients forced us to invent rational numbers. Rational coefficients, something like x squared is 2, require us to, or even integer coefficients for nonlinear equations require us to have irrational numbers. Well, we'll prove that the square root of 2 is irrational if you haven't seen it. But if you have polynomials with real coefficients, sometimes they don't have solutions like this one. So now you say, well, fine, let's throw in the number I. Which is the solution of this equation, and now you can consider polynomials where these guys are complex numbers. And you might think that you have to invent yet more numbers, hypercomplex numbers or something, for all polynomials to have solutions now. But that's not true. If you take a polynomial with complex coefficients, it always factors into linear factors. So in particular, it has to have at least one solution. Right? And that's the first magical property of complex numbers, is that any polynomial with complex coefficients must have complex solutions. They can recur, of course. You can have an equation like x minus 1 to the n equals 0, which has only one solution, but it can factor into linear factors. That's the first piece of magic about complex numbers. And the proof is extreme. This is not an easy thing to prove. It's called the fundamental theorem of algebra. And we will prove it in class using integration in some fantastic way. Right? So the proof is extremely subtle and involves quite a lot. There is an algebra. What's the second reason to consider complex numbers? Well, you know, on the real numbers, you can add real numbers, and there's a 0. That is the unit for addition, right? If you add 0 to any real number, you get the same real number. And you can do that on any vector space, on any real vector space, right? You can add vectors. You can, there's the 0 vector, which if you add it to any other vector, you get the vector you started out with. Every vector has a minus, such as an opposite of it. And if you add the two together, you get 0 and so on. But the real numbers also have multiplication, and multiplication also has division, right? You can, well, you can't divide by 0, so you have to be a little careful. And you can ask, can you invent a multiplication operation on vector spaces? Right? Now the dot product is no good because it takes 2 vectors and gives you a number, not another vector. Right? So can you come up with a multiplication operation that, just like this operation here, is commutative and associative and has a unit and is distributive across addition? And the answer is only if n equals 2. Well, of course, if n equals 1, we know that. But the only other possible solution is n equals 2. And the multiplication operation is you multiply a 2 vector by another 2 vector by the multiplication rule for complex numbers. You get here AC minus BD, and here, I guess, AB plus BC. Secretly, this is A plus BI times C plus BI. And the fascinating thing is dimension 2 is the only dimension other than dimension 1 in which you can invent such a rule for vector spaces. And the complex multiplication is the only multiplication that works, that turns this addition operation into that adds up to the vector addition and gives you this structure, what's called a field. If you're willing to give up commutativity of multiplication, you can also do it in dimension 4. And if you're willing to give up associativity, you can also do it in dimension 8. This was Gauss's invention. Before then, people were as skeptical of complex numbers as you are. But once Gauss drew this picture, then it's clear. It's just this plain old, plane that we're familiar with from geometry, and now you're inventing a multiplication operation on it. And if you don't want to consider it, you don't have to, but the fact that the plane has this thing has drastic consequences for things like analysis. And we'll see some of that in the class. The third motivation for looking at complex numbers, which is closer to the complex variables course, is what happens if we look at the geometric series, right? If you look at this function 1 over 1 minus x, you all have learned in your calculus class that this is 1 plus x squared plus dot, dot, dot going on forever. Is this familiar? Okay, but it's only valid if x is less than 1 in absolute value. And it's clear in some sense why this function should only converge, why this power series should only converge in this interval, because something very bad happens to this function if x equals 1. Right? And if you studied power series, you know that power series, they can't converge a little bit here and a little bit there and a little bit everywhere. They have to converge in an interval, diverge outside of that interval, and then the edges, there's some interesting behavior. So this is a power series in 0. It must converge in some symmetric interval about 0 and diverge everywhere out of that interval. And therefore, because at x equals 1, this guy has a singularity, there's no way you can push the convergence past x equals 1. Okay, so it's clear enough why this limitation on convergence must be true. And by the way, it's just outright false if you stick x equals minus 7 in. Right? It's not true that 1 over 8 is 1 minus 7 plus 48. Right? It's just wrong. Right? It's not that it's some kind of technicality. You'll get the wrong answer. Okay. But let's look at another function. Let's look at the function 1 over 1 plus x squared. Well, it's more or less the same thing as that. It's equal to 1 minus x squared plus x to the 4th minus x to the 6th plus dot, dot, dot. And now this is also valid only for x equals x less than 1, for the same reason that that power series. But now, this function looks like this. Nothing, absolutely nothing bad happens to this function at x equals 1 or minus 1. Right here, you can tell why it can't converge past minus 1. This function looks something like this, right? It has a singularity at x equals 1. But this function, nothing goes wrong at x equals 1. Why should it only converge? What's special about the point 1 and minus 1 if this guy only converges in the middle and nowhere outside? Right? It's incomprehensible. Looking at this function, you'd never guess it. On the other hand, if you look at this as a function of a complex variable, then at x equals plus and minus I, something very bad happens to this function. Just as this fellow is singular at x equals 1, this fellow is singular at x equals plus minus I. And we will prove, and it's part of the same rubric as power series converging only in intervals on the real line. Power series only converge on disks in the complex plane, and you can't possibly push it past the disk of radius. So power series in the real variable see the singularities in the complex plane, even if you only live in the real world. You don't care about complex variables. Once you study power series, you will be forced to consider the singularities in the complex plane because those determine convergence of the series even as a function of a real variable. Okay, and we'll see many other instances where if you study only functions of a real variable, you invariably run into the properties that those functions have on the complex plane. Right? So as a slight, as an advertisement again, and I am finishing, even if you only care about real variables, you will be forced to go to the complex plane and you will understand things in the complex. It makes sense once you go to the complex plane that are not apparent on the real line, and things become easy. If you want to find out more, join us in the class.
And just another personal plug, another class I highly recommend having taken it, having graded for it.
And Nick is going to be the TA.
Yes, so I'll be around next semester too. So definitely, if you have like any specific like questions from like a student perspective or whatever, feel free to reach out to me, or really a lot of other people as well. Do we any quick questions before we? Oh yeah. First.
How much like general working with complex variables are you going to teach in the class?
So we're going to start assuming you've heard of them, but the first homework exercise is lots of arithmetic of complex variables. So if you've seen, I assume you've seen them before, but maybe you're not, you don't have facility with them. Well, for the first week, we'll try to develop facility with complex numbers. So I'm not assuming, I mean, if you've never seen them before, you could still in principle do it, but I'm not assuming that you're good with them. We'll get you there. Is that also? Oh, yes.
I know I really appreciate how all this motivation for having complex numbers. Do we see them pop up in any other areas as far as like applications in?
Yeah, everywhere. I was trying to finish, so I missed my last. So we're going to do lots and lots of this. We'll see how far we get, right? It depends on the class. I never try to be too ambitious about how far we're going to go, because in fact, I just last week repeated the same lecture I did the week before because I thought the students needed to see it again. I'm happy to do that, right? That happens every once in a while, and it's not a problem. But there are applications for things like fluid flow in 2 dimensions. It turns out to be a lot simpler than fluid flow in 3 dimensions. Which is unfortunately where we live. It's fortunate, but at least we can solve the equation. There are a lot of things become simple. So there are a lot of things we can do. So the answer is yes, but I'm now feeling like I should go.
More information is better than less, for sure. Thank you. But thank you again. So our next speaker is actually going to be zooming in. We have Professor Dummett talking about the number theory classes that are being offered in this next semester. Do you have anything to share, or like share screen, Professor Dummett, or? I think your audio might be. I think your audio might be. No.
I can see him.
All right, is that better?
Yes, much better.
Okay, good. Yeah, I accidentally hit the power button on my monitor, so I'm not sure why that causes the microphone to disconnect, but who knows? Yes, so yes, I mean, I might as well throw in one thing about complex analysis, which is that I'm teaching it this semester. And one other thing is that Jonathan said that if you plug in 7 to this geometric series formula, that you get something that doesn't make any sense. If you would like to see me explain a way to make that make sense, come to my talk in the math club tomorrow, and I will explain how you can do things like this. Anyway, so number theory. So yes, number theory 1, math 3527. There are 2 sections of it in the spring. I'm teaching both of them. And so this course is as gentle as possible introduction to elementary number theory. So we study things like the integers, primes, factorization, divisibility, a lot of these things that I would imagine people have seen before at some point, usually in elementary school, and then again at some point later in their life. And the integers have this really wonderful property, which is that every positive integer can be written uniquely as a product of prime numbers, up to rearrangement. And so it turns out that this unique factorization property actually extends to other kinds of numbers that you might want to consider. For example, polynomials. Now, I know you might not think of polynomials as behaving like numbers, but if you think about just polynomials with real coefficients or whatever other kind of coefficients you like, integers, rational numbers, complex numbers, then in fact, you can show that polynomials also have unique factorization. There's a unique way to factor a polynomial up into irreducible pieces that can't be broken down or factored anymore. And so polynomials have a lot of similar properties to integers for that reason. You can do polynomial long division. You can compute greatest common divisors of polynomials, just like you can do with integers. There's a lot of analogies that are really very compelling between polynomials and the integers. And so the goal of the number theory course is to explore a lot of these connections and study what kinds of properties of integer arithmetic extend to other kinds of numbers, like polynomials. Another fundamental set of examples that we really spend a lot of time studying in 3527 are the Gaussian integers, complex numbers of the form a plus bi, where a and b are integers. These turn out to behave a lot like the integers. They have unique factorizations. There are things that you can call prime numbers in there that have a lot of the same properties of prime numbers in the integers. And so the theory is really nice. And so kind of understanding primes and factorizations and properties of arithmetic that extend to more general settings. That's the theme really of number theory 1. There's a lot of other things in that course as well. I know that because a lot of math CS majors take this class, I try to include a good amount of cryptography in this, since one fundamental tool that shows up a lot in cryptography is modular arithmetic and properties of powers, mod m. And so that's something that we spend a lot of time studying as well in this class. So do a little cryptography, try to talk about some computational things, how to factor large integers and why this is difficult, we think, getting into some of that fun computational stuff as well. So that's what we cover in the number theory course. And then there's a sequel course, number theory 2, which runs essentially whenever I can find time to teach it. I'm currently teaching it this semester. It gets offered once every couple of years, math 4527, where I do a bunch of other topics in number theory that are whatever the students in the class want me to teach. So that's just another thing to keep on the lookout for. And then also this spring, I'm teaching advanced linear algebra, math 4571. So this is intended to be a second course in linear algebra for students who've already taken a course like math 2331 or math 2341. So that's the linear algebra and then the linear algebra with differential equations course. So either one of those. If you've never taken linear algebra before, or if you've taken it somewhere else and don't have the official prerequisite, this isn't generally a big problem. Since in this advanced linear algebra course, I do everything from scratch. So starting from the beginning. But the emphasis is really a theoretical approach to linear algebra, to think about things in terms of vector spaces and vectors in an abstract way, and to really get comfortable with the general notion of a linear transformation, about computing eigenvalues and eigenvectors, about understanding inner products on very general sorts of spaces. And then studying various kinds of applications that you can do with writing down linear transformations in a particularly nice basis, in a particularly convenient way. And so linear algebra is a really fundamental tool. It shows up everywhere. It's incredibly important, in particular, if you're interested in doing machine learning. The more linear algebra you learn for that, the better. But physics, chemistry, engineering, of course, math and applied math, pure math and applied math, like everything uses linear algebra. And so I highly recommend, if you are going to be doing anything where you have to compute things on a computer, you're working with large amounts of data, linear algebra provides you a framework to understand the tools that you're using. And it has connections and shows up in almost everything. And so 4571 is a proof-based course. So it's really, the emphasis is really on proofs and very concrete problem solving. But if you are interested in the course, it's a really fantastic class. It's really great for students interested in any kind of science or engineering. Really, really good stuff. Okay. I don't think I have anything else specific to say. I mean, I'd be happy to give like examples of things that I talk about, like in 4571, some of the things that I throw in from other areas to talk about. I talk about least squares approximations. I talk about Fourier series and sort of how you can think about this in terms of linear algebra. I talk about singular value decomposition and how you can use this to do image compression on a computer. I mean, I talk about quadratic forms and how you can apply a lot of these ideas to do optimization problems and classify critical points, minima and maxima for functions of many variables. Again, something that is of extreme interest if you're trying to understand machine learning and how to train an algorithm in neural net to work through a bunch of training data to teach it things. That's all applied optimization. And so these are all things that you can understand with the framework of linear algebra.
Don't mean to cut you off, but just to keep on time with everything.
Yeah.
I know certainly, especially for number 31, a lot of students have taken number 31 already. So like
Yes.
the student perspective, if anyone has specific questions for students, basically like you throw a dart at a dartboard and you'll hit someone. So at least one person to have taken it. So thank you for going through. Let me make sure I'm in the frame here.
Yeah, I think I'm kind of like washed out here.
Thank you very much for talking about all of that. A lot of great courses, and definitely if you have like questions like specific to number 31 or linear algebra when it's offered next or whatnot, or advanced linear algebra, I should say, feel free to email him. Again, the email addresses will be up on the board at some point. So thank you very much.
Thank you.
Just gonna switch gears a little bit.
Next, we have Professor Carabin. Yes. The math modeling course. Is that correct?
Numerical methods
Yes.
for differential equations. Hi, everyone. Well, thanks for coming, and thank you for giving this opportunity, because last semester, I taught 2 semesters, I had quite a low enrollment. There was only 8 students, and 2 of them dropped. It's not that they couldn't withstand the pressure, they kind of weren't ready what it's all about. It's not
Speak a little louder.
Pardon me?
Speak a little louder.
Yes, I tried. So basically, the course is designed for mostly physics, engineering, and math majors who are intended to do some research in math physics and pursue that, mathematical physics. It is, I would say like this, once you take this course, you will understand the value of exact solutions. I don't know if you understood where I'm coming from. So numerical methods are fine, but that's what it is all about. I personally do exact solutions. And I was teaching numerical methods basically second time in my life, 2 semesters. So the course is such that basically those who took all calculuses, linear algebra and differential equation course, physics, and preferably knowledge in computer science. If you know Python, it's good enough. If not, then I help you. No problem. To write a small programs, there's nothing much there. So what yeah.
How much physics would you recommend the student has?
Basic physics. So if, for example, Hooke's law. Okay. So so basically you have to have good fundamental knowledge. The rest I will introduce. As far as differential equations is concerned, no, there is a very good course by Professor McCowan, he's teaching. However, I will do something which is not offered. For example, series solution. I remember we spoke about that, yeah, with Professor Jacob. There is no series solution. Series solution is good because you will have this in, if you take, for example, PDEs over there, when you solve, you basically transfer into ordinary differential equation and use series solution.
We just did that today in
Here we go.
PDE course.
Here we go. So therefore, one of the two equations over there which are very fundamentally important. It's Legendre equation and Bessel's equation. This,
What is this course number?
it is 3535. So Legendre and Bessel. Along the way, but this is the differential equation, numerical side. Certainly, I will introduce numerous methods. So starting with very basic Euler's method, improved Euler's method, and then would be three-term Taylor series method. What else is there? Runge-Kute method, Picard's iteration procedure. And then we will, this is all for first order and system of equations, and then we will go into second order equations. For second order equation, initial and boundary value problems. So boundary value problems, it's a second order. You cannot do this. You have to do finite difference method, unless you can transfer them into a system of equations and do that way. So we will play around one way or another way. So you will understand how it works. Either we will do that way, or we will go back and do it finite difference method. In the end, as I would call it, how to say, strawberry on cake, I intended to give you variational approaches, energy methods. Of course, you have to know a little bit of variational calculus. And I was wondering, do they learn in somewhere variational calculus? But if not, I will introduce you the basic principles, which would be enough for you to handle variational methods. Variational methods are Ritz method, and then Galerkin method, collocation method, and least square. Very powerful thing, very powerful, very interesting, and is used widely variational. And that is foundation for finite element methods. This is for engineers. Is there any engineer here? Any engineering student? No, all math majors. Nevertheless, finite elements, it's a package which you run. So if you never know what will be, yeah? Maybe you will end up working somewhere where you have to run this package. It's finite element method. So foundation for finite element methods, it's variational approaches, variational methods. So lots of work, take home mostly, because it's a robust work to do. All the exams, take home exams, lots of homeworks. It's a course to learn how to do these methods. That's about it. If you are interested in learning how to solve differential equation using various methods, that's the course to take and learn. Some interesting things will be there. For example, I regret that there are no engineering students. I will consider problems from structural mechanics, from very classic problems of, for example, from fluid mechanics, Landau's equation. I will go into bifurcation, which is also very interesting. Rob knows, but bifurcation, it's a very interesting situation. And also when it comes to nonlinear system of equation, Walter Lotke predator-prey problem, if you ever heard that system of nonlinear equations, it's a very important equation. It comes also in finance, if I'm not mistaken. Yeah, in finance, I think so. Yeah, as well this market systems. So that's about it. If you have questions, I will gladly answer.
So I would say that my background is more towards algebra, pure math type of thing.
Should you take this course?
Sure, but also which
I-
kind of course would you recommend for, I mean, my analysis background is not as strong as my algebra background, but I think I should take more analysis and learn about PDEs and that sort of numerical methods, just to know at least know more than zero about these things. So which of these courses in terms of numerical methods, PDEs and so on, would you recommend I take?
You've had 2341. Interpretation of linear algebra. Yeah, I think you're pretty qualified.
Oh, yeah, for
Either way.
qualification, you are, absolutely, it's not the issue. I don't know if you will be enjoying much because certain topics you will, I guarantee you.
Yeah.
Certain topics you will, 100%. But whether you will enjoy the entire course, because
Right.
all of a sudden you will come across to solving some problem which you cannot tie up to what you are doing. So what is this beam problem? He wants us to solve a beam problem or rotating disk problem. But there are so many interesting things in it, you will discover lots of physics which you for yourself, which you probably didn't know for some. And maybe in the future you will learn which will be helpful.
I'm unfortunately gonna have to cut off questions here just for timing, but I didn't mean to cut you off.
No. I was trying even to talk less than this.
Yes,
but-
no, very
So
much.
basically, that's about it, unless you have questions, I will disappear.
Thank you very much. And all the faculty's emails will be up on the board and very easily accessible. So if you have questions afterwards, feel free to send out emails. And just to keep the ball rolling, we'll actually be moving on to Professor Arbino, if you'd like to talk about 4020 and anything else.
So let's see, can I get rid of this screen?
Yes.
So Math 20 is the undergraduate research emphasizing capstone. The research can either be applied or pure. It's not restricted. In fact, one of the recent projects was Zoe Down, who did an evaluation of Northeastern University's bridge to Cockless. There's been one that's involves linguistics, but the structure will be offered in spring 2022. It needs to have 4 students to make. It's normally taught in the fall. I'll teach it now. If you want to learn more about it, well, I'll say something, but Nick took it and Zach Spell take it. So if you want to hear some complaints or whatever.
All good things, all good things.
They will help you out. So the basic thing is that there's a lot of presentation. It's almost a communication course. Doing presentations, learning how to answer questions and stuff like that. So there's a big presentation component. And you're presenting not only things you discover, but topics related to your topic because you become the expert on the topic in your class. And then there's a research component, which the main thing is to do a project. And in the second week, you send in a proposal. Basically, you coordinate with me and with a consultant in the math department. Actually, I think all the professors here are big consultants. And the consultants meets with you maybe half an hour a week or something like that. And the idea is that you don't have to do a topic new to math or a result new to mathematics, but it needs to be new to you. And the idea is that it should involve some thinking outside of just pulling down from the internet. So usually that gets arranged. It may be something involving computation. It may be understanding something fairly complex. The schedule a proposal week 2 after proposal, then extend to a progress report week 4. Then it's, you extend that and that becomes an actual report draft in week 8. And then students start practicing 30-minute presentations using the big screen, usually, or sometimes Blackboard. And then there's a presentation to the math department, usually on reading day. So it's a very intensive course. You'll present about once every 2 weeks. At first, some advanced linear algebra, then topics relevant to your project. If interested, please contact me. And the only Yarabino. And I'm at 526A, not Yale. Feel free to drop by. I'm often there 1:30 to 4. And I'll mention some of the topics that have come up. For example, Katie Lewandowski, who wasn't formally registered, she was actually doing a co-op, but she came to the class last spring. And her topic was machine learning for differential equation discovery. The advisor was Professor Kalina Kopos, who's in both biology and mathematics. Nick here did winter minimal services, not area minimizing. The consultant was Professor Zhu and Zhu, and he's now in the +1 program and continuing that project. Zuyun Li did algebra DNA sequences and DNA motifs. Is that your thesis? It's quite possible after this course, the 420, if you're not a graduating senior, you can take a junior senior thesis, and fairly often people have done that. That requires 2 semesters. The first can be 420. It could be Professor Jekyll's 5173. The
5131.
5131. It could also even be the applied math capstone 4025, which is also taught in spring. And then the second is you have a specific advisor. Usually the consultant becomes an advisor. So McPain, Queen Lee, I mentioned algebra DNA sequence of DNA motifs. That was Professor Harm Dirksen. Megan Hott, investigating viscous flow around a cylinder. Consultants were Professor McGowan and Professor Chris King. That was really at the level, it was a 420 project. It was basically at the level of a junior senior thesis, I thought. Noah Lichtblau did exploring the sum product theorem. His consultant was Evan Emmett, and Zhang Liu did solution to the Schrödinger equation in curved space-time. That was consultants Professor advisor was Professor Chris Beasley. Let's say sometime last fall, Zhang Liu did knots, braids, and configuration space. Matt Stevens, braids. Consultant was Professor Hei Wang. Matt Stevens did braids, knots, and non-invariants. Consultant was Matt Hogenkamp. Zhang Li again, and Zoe Don-Dimension. Consultant was Professor Phillips and the philosophy department. So it's, you have quite a lot of freedom to choose a topic. Usually people are working by themselves, in contrast to, say, 425 when there's small groups. John, I think is going to talk about that. I have some sheets here. Let's see, I'm not sure what to do with them. I'll probably drop some by each table and stuff, and I'll leave some of it.
And we can definitely send these out via email as well afterwards.
Okay. Thank you. Any questions? Yeah.
It's a little late for me now, but how would you recommend a student picks a capstone course?
So there's 3 capstones. There's 5131, which is Professor Jekyll's, which Professor Jekyll spends he will explain it, I think. But he does a lot of presenting at first, partial PDE. You should have had some PDEs, and it's math modeling. And then there's a chance to do, you do a project usually by yourself. And I do no presenting. Actually, I'm not presenting. So I do no presenting. Basically, each class the students are presenting. My work is mainly to make it work well, if you kind of work well together. So the 420, very research oriented, and the 425, John will speak about it, but it's more applied, doing stats and numerical analysis in groups of 3 or 4, although sometimes as an individual. So it's, if you want to do a more intensive research where you're working by yourself, 420 is probably a good choice. But if you're interested in kind of a more numerical for all 25. And if you want to do a little lighter research project, I think 5131, Professor Jekyll might object to that, but I think 5131 has a little more. You're learning some PDE and you're doing a project. Okay. Thank you very much.
I'm going to talk about it since I'm not teaching that in the spring. If you have any questions or any questions about the other courses, actually an advising nature, I can answer this.
About another capstone, you can also listen to our next presentation, Professor Lindy, who will be talking about the Applied Math Capstone 2025, as well as our Statistics and Stochastic Processes class.
Hello. So in some ways, let me start with the Math 4025, which is the Applied Math Capstone. Usually it is in groups because we usually get 20-some people for the course, and you usually work in a group of 3 to 5 people. Most people do statistics, but it doesn't have to be. For example, last spring when I did it, 2 people worked in machine learning. They worked with someone, one of them worked with someone in engineering, and one was working with material that they were doing through their co-op job. So it can be that. In the past, there's also been differential equation projects. So pretty much any kind of applied thing, but the typical thing is you're going to be doing statistics where you come up with a question you want to answer in your group. You then try to get data. You then update your question because you might not be able to get all the data, or you might not have a big enough question. So you update it. And similar to what Professor Yarbino was saying, you're in some form present every couple weeks, either in written form or in oral form. And at the end, you will present in 2 forms also. You'll be giving a little oral presentation, which is 15 minutes or so, and you'll also have a written report. So very open-ended. We don't really meet in class much. It mostly is you're working with your group, and we meet more informally. So let me stop with that. It's hard to describe it because it is pretty much open-ended, but any questions about that? I should say, as with all capstones, usually this is for juniors and seniors because it's near the end of just before you graduate. Yeah.
How do students find what kind of
Well, as I said, for me, question, how do they decide what applied math to research to do? So for mine, last spring, it was pretty much everyone was doing statistics. So we had just the first meeting was just walk around, talk to each other and see what you were interested in, and then form into groups and they try to figure out a question. So very open, but the first week or so, it's just figuring out who's in your group, what general type of thing do you want to do? So
Are you using data for all of your projects?
in some form. As I said, there were 2 people last spring that were doing machine learning, and they were using data, but they were trying to do a tweak on one form of machine learning. So it was more they were doing programming. So there was data involved, but it was more rewriting some things and seeing what you get.
When I taught the course, I taught it for several years, quite a while ago, but I always, to me, the difference in this between the other capstones was this used data. So I kind of wanted them to find a project that used data.
Right, so in some form it's always about.
Yeah, because I find the students today, they're not afraid of data. You know, us in the older generation, well, where am I going to find data? But the students usually have lots of sources.
Right, so in some form, it's convenient because it's in some form data to have had some statistics before or programming before, because you're going to be gathering data from online. But since you're in groups, it's not necessary that you particularly do. So if you don't know much statistics, just make sure in your group where someone else has done statistics. And then you'll do the non-statistics part, they'll do the statistics part. So very open. Yep.
Another quick question. How much sort of familiarity should students have, in terms of is there an expectation that everyone knows Python or, something to that extent?
No, so that's what I'm saying. So usually someone will need to know something like that just because you're getting data off the web. But as long as someone in your group knows it, then you don't necessarily. Last spring, pretty much everyone knew at least basics, but as long as you're in a group that they do. Yeah,
Just wanted to make a couple of comments that are relevant. First, all the capstones can count as upper level math electives. So you can do a capstone and separately take one of these courses if you want to do a project or some research. And the 5131 is kind of between the two courses. So it focuses on modeling the differential equations, and data is not required in the course. Many focus on the mathematical model itself. So it's less of a focus on.
so that's one thing that could sort of be in both, which is you can do differential equation modeling in this course, but it's more assumed that you're going off of data.
Use a text that just focuses on the model and may have data or may not.
Any other questions on the 4025? All right, so the other course I'm teaching is Math 4581. This is kind of a more straightforward one. If you've had Math 3081, which is the probability and statistics course, 4581 is kind of a straight continuation. So we start off with additional statistics. We do chi-square distributions. We do ANOVA. We do linear regression. We also do some moment generating functions, so we can sort of prove some of the stuff, sort of being kind of the quality there. And then we get into stochastic processes, which is basically just a sequence of probability distributions, which sounds hard, but pretty much anything where you're doing a sequence of probabilities, like you just toss a coin every minute, that's the stochastic process. And for that, we do kind of a survey, spend 2 or 3 weeks doing Markov chains, which is using matrices, 2 or 3 weeks doing queuing theory, which is how many people are standing in a line, and then a bit of just random processes in the background for stocks. So we get into a bit of stocks where we're assuming that stocks are a stochastic process. So there's some random movement up and down. So that one's a bit more straightforward. And then I usually try, when I'm teaching it, to add something in it. So after the statistics, I'll usually do a computer lab, which does some more complicated things. So we can't do multilinear regression in class because it takes a long time and it's not built into the calculator. So we put that into a computer lab and other things like that. So take the things that we did in statistics and do more complicated things that we can do with computer lab. And then for the other things, usually have a take-home quiz doing some more complicated elements that we did with queuing theory and Markov chains and stuff like that. So kind of explore where you might go if you're going further with this. Okay, so any questions on this?
What kind of student would you recommend this class to? So it's obviously a very applied class, very statistics based. So what kind of interest would you think would a student want to maybe explore this class for?
So the people who generally take it are just generally math people because it's an extension of 3081. Usually get a lot of people that are dual majors in math business because finance uses some of the stock stuff obviously and stochastic processes, and usually get a lot of math and economics majors because again we end up in stocks. In some ways that's why we ended up with stocks, because the first time I taught this, about a third of people were dual math and economics, so I figured to try to make it economics bit. And then usually there are some people who are in computer science, again, dual computer science and math. So in some ways, as Evan said, both statistics and stochastic processes are everywhere. So a lot of different places. But we don't get into, we're doing the more, as I said, we're doing more of a survey course, so we don't get into the real, we don't get into it really deeply. So more quickly. Any other questions?
Well, thank you very much. And just a quick comment, I've taken both 4025 and 4020, so if you want like a perspective like between the two courses or whatever from a student's point of view, feel free to reach out. The other quick thing I'll just sort of mention before we go to the next speaker is obviously there's a lot of classes that are being offered by the department, a lot of instructors, we couldn't get them all here today. So like just because some of the classes is being offered here doesn't mean it's not running. Definitely look look at sort of the course offerings. And if you have questions about any of the classes, obviously reach out to the instructors who are teaching the courses, but also feel free to reach out to students, myself, if you're on the unofficial math department Discord server, things like that, feel free to ask questions there. With that, I'll sort of pass it off for our next speaker, which is going to be a little bit sort of maybe less formal. Professor Jekyll, I don't know.
Yeah, and the math club permission, I'll just sit right here.
Yeah.
I don't know if I have enough words to justify it. So math 4545 is the partial differential equations course. It follows naturally, as you might expect, for 2341, which is differential equations and linear algebra. In fact, as a course, there used to be a two-course sequence here: the ordinary differential equations followed by the partial differential equations. Unlike 2341, where you see a variety of equations and techniques and applications, in the partial differential equations course, you focus on two equations. Applications are extensive, and the history that developed into the heat equation, wave equation is extensive. So that's the heat equation, wave equation, and understanding them entails looking at two other theories which enter into their solutions, and that's Fourier theory and Sturm-Liouville theory. The text I use does those very efficiently, so you can get very quickly to the solution techniques of partial differential equations. I also like to work in a little bit of traffic flow problems, just as a variety, have some variety of the PDEs that we consider. That's about it. I know Zach asked a question about one of the other courses. Is it focused on a qualitative approach like the dynamical systems, or more of a quantitative approach? I don't think quantitative is the right word for the PDE course, but it does focus on solution techniques. And there's a lot of problem solving differential equations. It's like a preliminary step if you ever want to take a more advanced course in partial differential equations, which can be more theoretical. This will give you lots of examples, lots of techniques. You'll be able to solve equations more readily involving PDEs than you might if you took a more theoretical course. I'm willing to answer questions about the course. And yeah, exactly.
I haven't taken the PDEs course, but I have taken math 4606, which has some overlap in terms of Fourier and a little bit dealing with those also techniques to apply differential equations. And I know that course is targeted toward a lot of applied people working in applied math and the sciences. I was wondering what the student base for
Student body is, I haven't looked at the numbers, but I'm sure it's at least 50% engineers. Because that was a requirement for engineers back when we had the quarter system a long time ago. Heat equation, wave equation, essential for engineering. Also, you get a lot of biology majors. I get a lot of combined majors. And even the finance people realize that, like in the Black-Scholes equation, behind it all is the PDE for arbitrage. So there's a variety of combined majors. It's without a doubt really important for our applications, as I just indicated, in a variety of fields. And I get feedback from students at co-op and also jobs, how they've used PDEs in their work. So I consider PDEs, can't get much of an argument. It's a fundamental topic for an undergraduate. So it's one of the basic things you should know about. But I'm going to stop short of saying this is an advertisement. If it appeals to you, by all means.
I'll just make a more general comment too. Hopefully you all know who Professor Jekyll is. But if you don't, he's the faculty advisor for the department. So if you have course related questions, like advisor type questions, yeah, send them to him. Just I realize some of you may have only met virtually or whatnot. Definitely, and again, always feel free to reach out to any faculty for questions or anything specific to their courses.
And Nick has taken this course, but he's taken every course.
Most. Actually, I did sort of general leading question for 5131. So obviously it's a graduate course, for students who, maybe have only had familiarity taking, undergrad courses, but want to go the route of taking the math modeling capstone. Should they be concerned? Is there sort of a significant difference in terms of difficulty level? Things like
Yeah,
that.
maybe a comment on that. 5131 that number goes back to when it was a hybrid course for the master's students and the undergrad students. In order to make that qualify in the graduate level, we gave it a 5,000 number. But for instance, number of students take it as an upper level math elective just to get another applied differential equations course, which essentially it is. And you only need 2341 in order to sign up for that course. So even though it has a grad number, unlike other grad courses where you need an override, you can just sign up for it. And Professor Yardino mentioned that partial differential equations is part of it. It's mentioned in the description, but it's not written into the enforced prerequisites. So, and you don't really need to know it in advance. When I teach the course, I develop anything you want to know about partial differential equations within the course, because we don't use Fourier series, we use just direct solution methods.
Thank you very much. Now is also a perfect time to note that obviously these are mostly undergraduate courses, but there are plenty of graduate courses as well that are being offered in the spring. So if you think that might be something of interest to you, definitely look at the course offerings, email the instructor, just to talk through the course, things like Geometry 1, Analysis 1. The Math Modeling capstone is running in the spring, taught by Professor Kopos. So a lot of great options there.
And don't be worried about if, it's a graduate course, can I enroll? Of any department, the math department is amazing. And if you think you're prepared for a course, you will get a chance to try a course. And all you need to do is ask the professor about an override, talk to the department, talk to Professor Jekyll, and the math department can usually work something out for you. Next, we have Professor Valiga, and talking about optimization of complexities.
And combinatorics.
Oh, and combinatorics.
But should be also
So I'm going to talk about two courses. One is combinatorial introduction to combinatorics. This is a course that is offered quite often in the spring and summer, and I'm not the only instructor teaching it. So I'm teaching it from time to time. Professor Albino is teaching it as well. So this is a course that is taken by computer science and mathematics students. And what is happening, since I want to link it a bit with the research that people are doing usually, the combinatoric problems seem very easy. They often related to the graph theory problems because you can have pictures, you can have very nice problems like so this is the book we are using, but we have very nice problems with pictures, and you think that the problems are easy in combinatorics. Well, the problems are really hard in combinatorics. And when people try to do research, they say, well, I'll take this problem and I will solve it, or maybe do a bit of progress. Well, this is very difficult. So this is why if you want to do any research in any area, like even algebra, speaking about algebra and more abstract, it's good to take a combinatoric course because it's everywhere in computer science, and you can find it and use it whenever you recognize it. You can use it. So I just put some sample problems that we use in this class. So this is our book. We go up to chapter 8. We stay very close to the book. We don't finish it. The applications are at the end. So if you go through this course, you'll be able to go deeper if on your own. But we start with permutations, and this is everyone can do this problem at any point, right? So we start very easy, we go to permutational multisets, and there we need the inclusion exclusion principle that we are going to apply in many forms and in many ways. We're going to learn different methods of solving problems. Yeah, it's not like just thinking hard and getting the answer, which often these problems seem to. And we touch a bit of theory of Ramsey, which is quite attractive to many people, and maybe the graph theory course is going to go a bit deeper into that. And lattice path toward the end of the course, which is also about counting how many paths you have, for example, under this diagonal, and you have formulas for doing that. And we don't use just pictures. We're also going to talk about a sequence of numbers. So you can see them coming naturally and getting formulas from series in different ways. We have different sequences, and for example, the Catalan numbers we use generating functions and that are going to be used in understanding this sequence of Catalan numbers. So these are just some snapshots from the course. Now, from organizational point of view, we have I have also the syllabus available, but we have 3 tests, a final exam, and a lot of homework. As people know me, I give a lot of work, and we have class problems, homework, and so if you want to learn it, you will be working hard on it. So this is about this. I don't know what the other file is. If I can get it.
All the all be up there along the top.
Yeah.
The syllabus.
So I prepared the syllabus for this class as well. But so this is just a very short syllabus. This is optimization and complexity class. This is a graduate course, and this course is taken by various type of students: undergraduates, master students, PhD students. Some students come from engineering departments with very little background in mathematics. Okay, so this means that, for example, the algebra, linear algebra is going to be introduced as we need it. It's a very nice course that put together algebra and real analysis. And we start with the simplex method, and we use then the polygons and we look at them from an analysis point of view. So if you ask why I'm talking about this can be taken by undergraduates. The undergraduates taking this course in the past were the best students in the class. It's all we need is real analysis type of base and linear algebra, but just basics. Okay, and it is like this weekly homework, and we have tests as well. But you need to have experience with proofs. Okay, so if you have all these 3 elements, you do very well. But it's a fun class that combines these areas. And we don't use any computer programming because it's done from a pure math point of view. Even though, because my, let's say, the background is commutative algebra, last year I introduced commutative algebra methods, which solve integer programming problems. So this is more modern kind of optimization. So if you're interested, I hope next semester I'm going to talk about commutative algebra, which I really want to teach in fall. But not now. Okay, so this is all I have. Any questions you have? This one.
Have a slight change. Professor Libner, would you mind going after Professor Toledano? Is he? He's on Zoom. Yeah, he's on Zoom and he has to go in a moment. So apologies. And certainly we are running a few minutes late today, so I do apologize about that to all of you. But we have 2 speakers left. Let's see. Let me just. Okay, there we go. Hopefully that. First, Belladonna, can you hear us?
I can hear
Awesome.
you at least.
Fantastic. So thank you for coming. So our next speaker is Professor Toledano, talking about advanced probability and statistics, Math 3181.
Okay, thank you. Thanks a lot. And I want to first of all apologize that I'm not here in person. I'm in, as I mentioned to Nick, I'm in an NSF panel, which is running 12 hours a day, yesterday, today, and tomorrow. So it's a little bit crazy. So I really would like to be there in the room to actually, in particular, to see you guys. But you know, that's life. Yes, I wanted to say a few words about this 3181 class, which has been running, I don't know, couple of years, maybe a little bit more than that, and to explain what's in it, what's not in it, and why, in some sense, this the advanced name is a little bit of a misnomer. In that, so the class initially started life as a sort of an honors version of 3081, which is probability and statistics, and then somehow was detached, and then someone, not me, chose this word advanced. But it's still supposed to be, and it is, a first class in probability and in statistics. So you're not expected to come in with already a knowledge of probability. I'm usually students come in with some knowledge of statistics, say AP statistics from high school, but none is expected, and certainly none is expected from probability. So maybe I'll say a few words about probability, and then how the 3181 is different from 3081. So probability, I mean, is a study of random phenomena, random fluctuations, and which are all around us in data science, in the atmosphere. I mean, if you feel the temperature on your skin is because there's air particles bouncing randomly on your skin. Same thing for air pressure. And so probability is really the study of those, and it's a subject that somehow, perhaps for evolutionary reason, is not really well wired in our brain. So it's a subject which is very, very, in some ways, it's both gorgeous but also extremely counterintuitive. So a lot of people, me very much included, tend to get probability computations wrong the first time they do them. And so this is why a good course in probability is a good idea to really train your brain to think clearly about those. And so there's a standard example. There's a little problem that I discuss in class usually, which is, a family has two kids. You were not allowed to go into the house. You're just told one of the kids is a girl, and then you're asked, what is the probability that the other kid is also a girl? And I don't know. Do you guys actually have any? What do you think the answer is?
1/3. 1/3.
One third. Okay, so some at least one person knows the answer. Okay. And now, what if so it's usually some people say 1/2, but then the correct answer is 1/3. But it gets trickier if I were to say, suppose one of the kids is a girl who was born on a Tuesday. What is the likelihood that the other one is a girl?
13/27.
Okay. All right, so whoever answered that does not need to take the class. Okay. You get a dispensation, but so part of the class is exactly to discuss why the answer is not 1/2 for the first question I asked, and then not 1/3 for the second question I asked. So we tend to spend some time discussing things, Monty Hall type problems. And for example, there's also beautiful two envelope paradox, which I don't know if you know this, but if I were to tell you there are two envelopes with unspecified amounts of money in them, one has an amount and the other one has twice that amount, and you're put in front of them, and the paradox is, I tell you, choose one, whichever one you like, and you get to keep what's in it. So you're about to open, say, the one on the left, and then you tell yourself, okay, just a second. So the other envelope has, say if there's, suppose I think there's $50 in the one I'm about to open. Well, the other one has either 25 with probability 1/2, or what did I say, 50 or 100. So on average, the other envelope should have 125 divided by 2, right, which is greater than $50. Therefore, I should switch. So then I put the left envelope down and I say I'm going to go for the right envelope. And now I ask myself, just a second, but whatever the amount is in this envelope, the right envelope is, I can do the same computation, right? So the other envelope is supposed to have half that amount with probability 1/2, or twice that amount with probability 1/2. Therefore, on average, it should have a higher amount. So I'm going to switch and then switch and switch and switch. And so this is a so-called two-envelope paradox, which seems to fly in the face of the fact that, not knowing anything about the two envelopes, the expected amount in one should be the same as the expected amount in the other, because the envelopes are exactly identical. So again, part of the class is devoted to discussing problems like that. So this was just a kind of somewhat accelerated introduction to probability. There are in probability, so there is some overlap with what Professor Velice just explained. There's in probability, there's a lot of counting. I mean, for example, seating arrangements around the table come in with probabilities. If you like combinatorics, this is one thing that you might enjoy. And then, yes, I wanted to say so everything I've said so far is more or less common to 3081 and 3181. So in what ways do they differ? So again, they do not differ in terms of the prerequisites for students. Where they differ by is somehow the appetite that students may or may not have for a proof-based class and for going more into depth into the math. So 3181 is maybe less proof-oriented. There's less proofs, and 3181, so the one I will be teaching next semester, dwells more on the math. And the beautiful thing about probability is you can prove really important theorems without not too much technical baggage. You just have to budget some time to do that. So if that is your taste, if you want to, I am a mathematician, so I like to look inside and behind of things. So if that is your taste, if you do like mathematical proofs, then this might be the place for you. So there's one, for example, standard result. Well, standard means one kind of pillar result in probability theory, which is called the central limit theorem, which explains why in a lot of natural phenomena, the bell curve, the one that some tests are graded on, appears. And so that's called the central limit theorem. It's one of perhaps the most important theorem result in modern probability theory. And then that is in 3081 that gets mentioned and discussed. And in 3181, we spend a lecture and a half discussing the ins and outs of the theorem and actually its proof. Again, the proof is not technically very arduous, but it does require spending a little bit of time developing the correct tools and then applying them to the problem. Maybe other differences, there's a little less attention to statistics in 3181. My experience with that having been to date, I've taught this 4 or 5 years, that students come in with some background in statistics, often through AP statistics, and so somehow, but not as much grounding in probability. So I prefer to given that time is finite, I prefer to give them a bigger grounding in probability rather than in statistics. And another difference is, at least last year, we ended the class with a topic called Markov chains, which is a super important topic in probability theory, and is used everywhere in economics, in game theory, in biology. So in lots of applications of probability, Markov chains are very relevant. And then one application of this, one very real world application and a real life application of Markov chains is the algorithm that fuels the Google search algorithm. So the algorithm is called the PageRank algorithm. So that's what made the founders of Google, initially made them billionaires. It's called the PageRank algorithm. And the reason why Google is such a a more effective search engine than others. And so at the end of the class, we'll spend some time talking about Markov chains in general, and then we'll then apply that knowledge to studying specifically the PageRank, so the algorithm that powers Google.
So much, Professor Toledano. That was a great overview of the difference between the two courses, and I'm glad that any students here should have a little more understanding of which one they want to take between the two now. And if they have any more questions, they can definitely follow up with you or with us. We can all, Nick or I can definitely find contacts for students for any of these courses. And next.
Yeah, so let's give a round of applause.
Can I just say one thing? One thing I would recommend, is maybe if anybody in the room has already taken 3181, after I'm gone and I can't hear, you can ask them what they thought of the course. I mean, that's probably the best way to get a sense of whether you would like the course or not, is just ask somebody who's already taken it to get a better sense of the class.
Yes, highly recommend that. Quinn Arbolanta has taken it, so definitely ask him.
Yes, I remember Quinn very well. Yes.
Again, thank you again. Really appreciate it. Hopefully you get some more interest for the spring semester. We'll definitely keep pushing it. This class. So.
Thank you. Thank you for the opportunity.
One more talk today.
Last but not least, Professor Lipner. Talking about a new graduate course.
Okay, so first of all, let's get rid of Valerio. He doesn't need to anymore.
Bye-bye.
Bye. Just blank the video.
So just a little bit of background. In the past 3 or 4 years, every semester I've been teaching sort of a graduate level topics course for mostly my students and my PhD students and students around similar interests. And each semester we pick some interesting topic, and sometimes it's a reading course format that the students do the presentation, sometimes it's more like a lecture-based format. And this, like the coming semester, I chose a topic that I think is accessible, easily accessible to interested undergrads. So this isn't a course that would run every whatever. This is a one and only kind of, probably won't teach something like this in 5 years because there's so many other things that we do a different topic every semester. So this particular course will cover, we'll start from what is called the Banach-Tarski paradox, which you may or may not have heard about. If you haven't heard about it, it's basically math's solution to overpopulation of the world and solving the food, like how to provide enough food for every person. Because what it tells you is basically you can take an orange and split it up into 5 pieces and reassemble those 5 pieces into 2 oranges of equal size and quality from the original one. So quality also? Well, I mean, mathematically speaking, it's going to be a solid orange, probably juicy, and the same number of seeds and whatnot. Jokes aside, this is a very counterintuitive but true fact. It's not a paradox. It's a true fact, which is very counterintuitive. And the course will be revolving around counterintuitive but true facts like this. They often stem from the notion of infinity, how you can take 2 infinite things and they're still both infinite. That's kind of the simplest, like the even numbers are infinite, the odd numbers are infinite, but together they're just as infinite as on their own. So similar ideas, but in a much more complicated and involved settings is what makes these things work. Now, this is a very much not a typical undergraduate course in the following sense. In a typical undergraduate course, you study one subject and like go deep into it. And this particular topic, and which is why I really like it, is it sits at the intersection of at least 4 different mathematical fields, namely analysis, algebra, probability, and even a little of graph theory, and even geometry, so maybe 5. And so what we do in this course is pull techniques and knowledge from all of these fields to apply to like one kind of circle of ideas. And I think that's like really beautiful in math, and completely different ideas can interact and yield something useful. Now, in terms of the format of this course, this will mostly be lecture. I will try to provide like some practice exercises, but it's mostly just like you listening to what I think is like super interesting math, but it's very proof heavy. It's like a lot of definitions. You'll have to kind of absorb a lot of notions and ideas. And in terms of creating requirements, what I have at the best idea is that every student will be asked to like produce notes from certain lectures. That's kind of the level of creating I'm thinking about right now. So it's going to be like a conceptually difficult and heavy math course, but not very heavy on requirements. But I would still only recommend it to people who are like, you know, looking to go on to a master's, like learning more deep math. This is like, I think is a great opportunity to learn something that wouldn't be normally taught in an undergrad course, but is definitely like learnable. I have taught once a similar course that was in Hungary, where I came from. And at that time, like sophomore, junior level undergrads took it, and they did just really well. But of course, comparing, so that would probably compare to like a more like an advanced junior / senior type of undergrad here in this program. Is just in Hungary, the math majors have to take a lot more math courses from freshman year. So that's okay. Yeah, so that's all I really wanted to say, and happy to answer any questions.
And I will say, Professor Lipner is on the Discord server. So
oh yeah,
if you
so
have
be
questions,
careful what you write.
Well, yes, that, but also if you have any specific questions, you know, obviously you send an email, but also just send a message on Discord or whatnot. So, quick question.
Hi.
Quick question. We were talking about that this class require like couple like area from the math, and so I remember you said like geometry. To be honest, like last time I take serious geometry was, well, that was before ninth grade.
So serious geometry, not serious geometry. Like this will be only involving kind of you know, the kind of question that I anticipate talking about in this course is I give you two polygons of the same area. Can you cut one into pieces and glue it into the other one? Maybe the same with like spatial shapes, like a polyhedron. That's probably the level of geometry. And I mean, the other kind of geometric idea is like when you take the orange into many pieces, you have to kind of move them to reassemble the orange. So we will be talking a lot about isometries of 2 and 3 dimensional space. So like rotations, translations. But these are all very elementary ideas. And you know, actually probably 9th grade is about the time you learn about these things. So it'll be maybe nice revisiting your high school studies.
And anymore, I'm afraid we're gonna have to cut you off. It looks like there's another class that's.
We have room for 2 more minutes.
Oh,
So then I do want to say one more thing,
Yes.
not about this, but you may know that I also organize a math dialogue, a dialogue of civilizations, summer 2. It's approved, so it's gonna run. Signups aren't gonna be open before mid-November, and I just got an email asking about what's going on. So if you are thinking about it but you don't see it, it's because none of the dialogues will be open up until mid-November, and then the decisions of like who's coming on the dialogue will be like late December. But once the signups are open, we will be starting to look at your applications. So please apply sooner rather than later. And of course, I'm also happy to answer questions about that. Thank you very much.
So that actually concludes this information session. Sorry for going a few minutes over, but we are concluding. And if you have any questions at all, we'll send out information, we'll send out the recording, anything like that.